Imagine a universe utterly alien to our own. No stars, planets, or even the familiar atoms that constitute our world. Instead, picture a reality brimming with pure, uncontainable energy, a chaotic sea of quantum fluctuations. This is the primordial universe moments before the Big Bang, a realm governed by laws we are only beginning to glimpse. In this epoch before matter, energy reigned supreme. It crackled with unimaginable intensity, constantly transforming and shifting within the fabric of space-time. The very forces that govern our universe, gravity, electromagnetism, the strong and weak nuclear forces, were all intertwined, unified in a way we are yet to fully comprehend. This primordial soup of energy, though devoid of the structures we observe today, held the potential for everything. Within its chaotic dance lay the seeds of galaxies, stars, planets, and even life itself. The question of how this transition from pure energy to matter occurred is one of the most profound mysteries in cosmology. From this state of pure energy, the universe embarked on its journey of expansion and cooling, the event we call the Big Bang. It wasn't an explosion in the conventional sense, but rather an expansion of space itself, an inflation so rapid and profound that it boggles the mind. As space expanded, the energy density began to decrease, causing the universe to cool. This cooling was crucial, as it allowed for the separation of the unified forces that governed the early universe. Like a cooling metal transitioning from liquid to solid, the universe began to undergo phase transitions, each one marking a profound shift in the nature of reality. One by one, the fundamental forces separated. Gravity, the strong force, the weak force, and finally, electromagnetism. With each separation, the universe became a more differentiated, complex place, setting the stage for the formation of the particles that would eventually give rise to atoms. The first few minutes after the Big Bang were a period of intense activity, a cosmic particle accelerator of unimaginable power. As the universe continued to cool, energy began to condense into matter, following Einstein's famous equation E=mc2, which reveals the intimate relationship between energy and mass. Out of this energetic soup emerged a flurry of fundamental particles, quarks, leptons, bosons, the building blocks of matter as we know it. These particles, born from the cooling energy, interacted with each other at incredible speeds, constantly colliding and annihilating in a chaotic ballet governed by the laws of physics. Yet amidst this chaos, a sense of order began to emerge. Quarks, the particles that would eventually form protons and neutrons, began to clump together under the influence of the strong force, one of the fundamental forces that had separated from the unified force during the Big Bang. As the universe expanded and cooled further, a critical threshold was reached. The temperature dipped below the binding energy of quarks. This meant that quarks, once free to roam and collide, were now trapped by the strong force, bound together in groups of 3 to form protons and neutrons, the building blocks of atomic nuclei. This era, known as baryogenesis, marked a turning point in the early universe. For the first time, stable particles of matter, protons and neutrons, existed in abundance. Yet the universe was still too hot for these particles to form atoms. The electromagnetic force responsible for binding electrons to atomic nuclei was still too weak to overcome the immense thermal energy. The universe was now a sea of protons, neutrons, and electrons, along with photons, the particles of light, constantly interacting and exchanging energy. This period, though teeming with the building blocks of matter, was still a far cry from the structured universe we observe today. Finally, after approximately 380,000 years of expansion and cooling, the universe reached another critical juncture. The temperature dropped below 3000 Kelvin, roughly 5000 degrees Fahrenheit. This marked the beginning of the epoch of recombination, a period when the universe transformed from an opaque fog of charged particles to a transparent tapestry of neutral atoms. At this lower temperature, electrons, lighter and faster than protons and neutrons, were finally slow enough to be captured by the electromagnetic force of atomic nuclei. Protons, with their positive charge, attracted negatively charged electrons, forming the first atoms of hydrogen, the simplest and most abundant element in the universe. This era of recombination was a pivotal moment in the history of the universe. The formation of neutral hydrogen atoms had a profound effect on the universe, making it transparent to light for the first time. This freed photons to travel unimpeded across the cosmos, carrying with them a snapshot of the early universe. The birth of the first atom, a simple hydrogen atom, may seem inconsequential in the grand scheme of the cosmos. Yet this seemingly insignificant event marked a profound shift in the evolution of the universe. It signified the transition from a universe dominated by radiation to a universe governed by matter, setting the stage for the formation of stars, galaxies, and all the structures we observe today. This first atom, forged in the crucible of the early universe, was not merely a collection of particles, but a testament to the elegant laws of physics that govern our cosmos. It represented the triumph of order over chaos, the emergence of complexity from simplicity. The formation of the first atom was not the end of the story, but rather the beginning. It marked the dawn of a new era in the universe, an era where matter, now bound together in the form of atoms, could begin to clump together under the influence of gravity, eventually giving rise to the stars and galaxies that illuminate the cosmos. While the Big Bang model provides a compelling explanation for the formation of the first atom and the evolution of the early universe, it is essential to acknowledge that our understanding of these early epochs is still evolving. Scientists continue to explore alternative theories and refine the Big Bang model based on new observations and theoretical advancements. One such alternative is the steady-state theory, which proposes that the universe has always existed and has no beginning or end. Another is the ekpyrotic universe model, which suggests that our universe was created from the collision of two three-dimensional universes in a higher dimensional space. These alternative theories, while intriguing, lack the robust observational evidence that supports the Big Bang model. Nevertheless, exploring these alternative perspectives is crucial to ensure that our understanding of the universe remains dynamic and open to revision as new data emerges. Section 8. The Cosmic Microwave Background, an echo of the early universe. One of the most compelling pieces of evidence supporting the Big Bang model and the formation of the first atom is the cosmic microwave background, or CMB, radiation. This faint afterglow of the Big Bang, discovered in 1965, provides a snapshot of the universe as it was just 380,000 years after the Big Bang, during the epoch of recombination. The CMB radiation, distributed uniformly across the sky, exhibits tiny temperature fluctuations that correspond to regions of slightly different densities in the early universe. These fluctuations, amplified by gravity over billions of years, eventually gave rise to the large-scale structures of the universe we observe today: galaxies, galaxy clusters, and cosmic voids. The discovery and subsequent study of the CMB radiation have revolutionized our understanding of the early universe, providing strong evidence for the Big Bang model and the processes that led to the formation of the first atoms. Section 9. Implications for our origins, connecting the dots. The formation of the first atom, a seemingly distant event in the vast expanse of cosmic time, has profound implications for our understanding of our own origins. Every atom in our bodies, every element that makes up our planet, and everything we see around us was forged in the hearts of stars or during the cataclysmic explosions that mark their deaths. We are, in essence, stardust, connected to the very fabric of the cosmos through the atoms that make up our being. Understanding the processes that led to the formation of the first atom allows us to trace our cosmic lineage back to the very beginning of the universe. By studying the early universe and the formation of the first atom, we gain a deeper appreciation for the delicate balance of conditions that allowed for the emergence of complexity and life in the universe. It highlights the interconnectedness of everything in the cosmos and underscores the profound implications of understanding our place in the grand scheme of things. Section 10. Unraveling the mysteries, the quest continues. While we have made significant strides in understanding the formation of the first atom and the evolution of the early universe, many mysteries remain. The precise mechanisms that drove inflation, the period of rapid expansion immediately following the Big Bang, are still not fully understood. The nature of dark matter and dark energy, which together constitute about 95% of the universe's mass energy content, remains elusive. And the question of whether our universe is unique or one of many universes in a vast multiverse continues to intrigue scientists and philosophers alike. The quest to unravel these mysteries continues to drive scientific exploration, pushing the boundaries of our knowledge and challenging us to confront the profound questions about our place in the cosmos. Each new discovery brings us closer to understanding the fundamental nature of the universe and the incredible journey that led from the void to the vibrant tapestry of stars, galaxies, and life we observe today. Section 11. Conclusion. A universe forged from the void. The journey from a universe of pure energy to the formation of the first atom is a testament to the awe-inspiring power and elegance of the laws of physics. It is a story of cosmic evolution, of the emergence of complexity from simplicity, of the delicate balance of conditions that allowed for the universe as we know it to exist. As we continue to explore the cosmos and delve deeper into the mysteries of the early universe, we gain a deeper appreciation for the interconnectedness of everything around us. The atoms that make up our bodies, our planet, and everything we observe were forged in the hearts of stars or during the cataclysmic events that shaped the early universe. The formation of the first atom was not merely a scientific curiosity, but a pivotal event that set in motion the chain of events leading to the formation of stars, galaxies, planets, and ultimately, life itself. It is a story that continues to unfold, reminding us of the vastness of the universe and the endless possibilities that lie hidden within its depths.